matches, that is the keyword similarity within each topic. So we form a topic hierarchy, and within wireless we have keywords such as electromagnetic, communication, and network. Within networks, broadcasting, transmission, communication. For Wi-Fi, wireless protocol, broadcast, and so on. Now notice that broadcast and broadcasting have overlap. Okay, and so networks and Wi-Fi, even though the actual strings themselves have no match or similarity, the keyword networks, the interest key networks, and the interest Wi-Fi have a similarity measure of 2. And here we see that wireless and Wi-Fi have the strongest similarity. Networks and Wi-Fi have a similarity level similar to that of radio and Wi-Fi and wireless and radio, and the weakest link here is between wireless and networks. And this matches or jives with, hopefully, our intuition of what a similarity measure is between Wi-Fi and networks, where Wi-Fi is a subset of networks, but wireless and networks have some overlap, but neither is strictly contained within the other. Now we can actually form a concept hierarchy by bottom-up hierarchical agglomerative clustering as well, starting with ground level or leaf keywords such as truth and fact, or evidence, factual, statement, and agglomerating them to form arguments and statement, then combining that with certification to form argument, statement, and certification, and then with truth and fact to form a master class of aspects of argumentation. So if we do this, we can actually drill down, as with online analytical processing, and actually expand the set of books into subgenres, and similarly with our hierarchy of words, phrases, movies, and then comedy books and each subcategory. So what we'd like to do is actually predict friendship links. And the task we've formulated is a machine learning task, rather a classification task that can be solved by means of supervised inductive learning. The specific task is to predict for a candidate pair A and B whether there's an actual friendship link extant in the ground truth network. So the set of instances is of the form user A, user B, the IDs of A and B, and a class label, which is 1 if and only if there's a link from user A to user B. So this is concept learning of the existence of a friendship link. What we'd like to do to represent these instances is generate interest-based features constructed using different levels of abstraction in our ontology, and graph-based features which consist of the results of analysis. For example, the shortest alternate distance between A and B, and the reciprocal distance from B to A. So the different levels of abstraction in our ontology start with a root level class and can be refined by drilling down in the organized set of keywords that we've been able to glean from our sources. And this is how the ontology is actually constructed. The other aspect of features, the other type of group of features, are interest-based numerical features, which are based on the interestingness measures for association rule mining. So in association rule mining, we can think of each interest as an item set, where the item set's elements are the interest holders. Okay, so for example, if we say have an item set that corresponds to Dell notebooks, that's a subcategory of computers, and the interest holders are all the people who list Dell notebooks as one of their interests. If two people have a common interest, they're going to be co-members of that, and so we want to find frequent closed item sets, as with traditional association rule mining. There are 8 interestingness measures that are calculated based on probabilities, which are ratios of the number of interests held by user A divided by the total number of interests by user B and by both A and B. Now, in Pannington's survey of interestingness measures, he identifies a number of interestingness measures, including these 8: support, confidence, which is directed, lift, conviction, match, accuracy, and leverage. And my doctoral student, Walid Aljandal, in his dissertation, looked at techniques for normalizing these interestingness measures based on the size of the item set. So in certain situations, we might actually care about whether it's significant that 2 people are interested in computers versus Dell notebooks. The latter set is a much smaller set than the former. And in the semantics of that of interest holders, the sharing of a rarer interest is more significant. And for details, I'll refer the interested reader to Walid's dissertation and to a recent paper in the AAAI Spring Symposium series on the social semantic web. Now, in our original work, we looked at identifying graph-based features that are user single-node dependent, pair-dependent, and the user-dependent or single-node dependent features include in degree of A and B and out degree of A and B. So if we're interested in looking at B as the candidate target friend, right? So A is considering adding B. B might be the publisher of or author of a web comic. So it stands to reason that B would have a very high in degree because he or she has a very popular blog. Similarly, A might be a person who adds people habitually and has a lot of friends, and they have a very high out degree, and that might condition us positively or raise our conditional probability or our belief in the existence of a link to a new candidate friend B. There are 4 senses of mutual friendship where we can look at a friend C that A has named that also names B as a friend. That's the first type. One that B has named that also names A as a friend. That's the second type. The type 3 mutual friendship is the more traditional sense where A and B both name some mutual friend C as a friend, or the type 4 mutual friendship, which is there exists some C that names both A and B as a friend. And we can also look at reciprocal distance. That is, if B has already named A as a friend, then it's very likely that A is going to reciprocate. And in some networks, as I mentioned, LiveJournal, Facebook, for example, reciprocation is required for the social network to actually register an extant relationship. So now for our results, our experiments and results. Does the ontology actually help? What we've assumed is that LiveJournal represents a complete social network graph. And the features of this graph include interest-based numerical features with and without our graph-based features. What we've done is to run every experiment 5 times. In each replication, I equals 1 to 5, we construct a training set DI that has 3,700 links that are drawn from a more evenly skewed, that is not representing the original distribution of 1 to 1 to 99, but 50% positive and 50% negative. 3,700 links. That's the training data set. Now the validation data set is a representative data set relative to the original. It is 1,850 links with 1% positive and 99% negative, and a test set that's also from the same distribution. For our validation and test sets, we estimate graph features